today. Okay, the speaker today, this is Professor Bogdana Oliynik, and the talk is joined here with Professor Oksana Bezushchak. Both ladies, they are from Kyiv, from two different universities. So I joked before the talk with Bogdana that in Russia there is a joke, how many diplomas do you need to be intelligent? And the answer is 3 diplomas. And the question is, which specialist, not which specialist, but who has to have the diploma? You, your father, and your grandfather. Yes. So Bogdana, she has Doctor of Science. Her father, Vitaly Suchansky, also was Doctor of Science. Her husband is also Doctor of Science. And her joint author, Oksana Bezushchak, she is also Doctor of Science. So this means that they are really very, very intelligent. But also, if you, the people from the Western, they don't know what this means, Doctor of Science. So you should open Dr. Dolittle and see the beginning that in his door it was written DM Dolittle. DM means Doctor of Medicine, and this means that he is a very, very clever person. So the same holds for Doctor of Sciences. But okay, please, Bogdana.
Thank you very much, Professor Jensky. First, I would like to say many thanks to organizers for inviting me to this seminar. It's a great pleasure for me to have a talk today. And my talk will be about unital local matrix, algebras, Steinitz numbers, and primary decompositions of unitary local matrix algebras. Talk will be in my talk, I use a joint research with result of our joint research with Oksana Bezushchak, also from Kyiv. So let V F be ground field, and this talk we consider associative unital F-algebras. And following course, F-algebra A with unit 1 is said to be a locally matrix algebra if an arbitrary finite collection of elements A1, A2, and so AS from A lies in subalgebra B. Okay, better. Lies in the subalgebra B with one of the algebra A that is isomorphic to a matrix algebra M and F for some positive integer n. And we assign a Steinitz number to an arbitrary unital locally matrix algebra A. So first, I recall definition of Steinitz number. Let P be the set of all primers. A Steinitz number, sometimes Steinitz number is also called a supranational number, is an infinite formal product of this form. Product of primers to some power, where P in the set of all primers. Where this power may be some positive integers, maybe 0, maybe infinity. And we also can multiply two Steinitz numbers in the following way. If we have one Steinitz number and we have another Steinitz number, so we can consider a product of these two Steinitz numbers, where this power equals RP plus KP if RP and KP positive integers and or 0, and equals infinity in otherwise. Denote by the symbol, the set of all Steinitz numbers. And it's easy to see that any positive integers we can also represent in this form. So, sorry. So all positive integers is subset of Steinitz numbers, and the numbers, Steinitz numbers that is not positive integers are called infinite Steinitz numbers. So if you consider the infinite Steinitz number, what may be how we can describe these numbers? Maybe situation where some power equals infinity, and maybe situation that we have infinitely many infinitely many non-zero powers. So in the second case, an infinite Steinitz number is called locally finite. So locally finite number is an infinite Steinitz number such that all of this power less than infinity. Gleam parameterized countable dimensional locally matrix algebras under the name uniformly hyperfinite algebras with Steinitz numbers. He considered sequences of finite dimensional algebras with special embeddings. This embeddings later in the Zaleski terms is called diagonal embeddings. And the main idea of this embedding is that if we have two algebras A and B, and we embed algebra A to algebra B, then one of A go to one of B. Okay. Later in the paper of Oksana Bezushyakmai and Vitaly Sushansky, this result was extended, this parameterization was extended to regular relational structures. And in series of papers of Baranov and Zhilinsky, uses Steinitz numbers to classify diagonal locally simple Lie algebras of countable dimensions. So all these papers and papers Gleam and my papers is Oksana Bezushyakmai and Vitaly Sushansky, and papers Baranova and Zhilinsky. In all of these papers considered countable dimensional algebras. And as partial case from this paper, we can formulate this theorem. If you have two unital locally matrix algebras of countable dimension, and A and B isomorphic, if and only if Steinitz number of A equals Steinitz number of B. So this is from, we can say that this is the result for this paper, and as a result of Baranova and Zhilinsky. Okay, and first question that we considered how we can generalize this definition of Steinitz number to uncountable dimensions, unital locally matrix algebras. And first definition, let A be an infinite dimensional unital locally matrix algebra over field F, and let B from A be the set of all positive integers n such that there is algebra A prime. This algebra is subalgebra of A. In this algebra contains one of algebra A, and algebra A prime isomorphic to some finite matrix algebra for some positive integer n. And after that, we consider the least common multiplier of this set, and the least common multiplier is called the Steinitz number of algebra A, and we denote by this symbol. Okay. And next question: is it true? Can we formulate this theorem in a case of uncountable dimensional algebra? Is this theorem will be true in the uncountable dimensional case or not? And so we have a negative answer. This theorem not true in uncountable dimensional case, but we have another characterization. So first, okay. First, first notation, first simple notation that we will use it if A and B be unital matrix algebras. Then the tensor product of two these algebras is also unital locally matrix algebra, and Steinitz number of product of algebra A and algebra B equals to product of Steinitz number of these algebras. So what characterization will be in the case if you consider infinitely dimensional algebras? Let now A be an algebraic system. The universal elementary theory consists of universal closed formulas that are valid on A. Sorry. The system A and B of the same signature are universally equivalent if the theory on A and the theory on B are coincide. So first theorem, let A and B unital locally matrix algebras, then A and B are universally equivalent if and only if their Steinitz number are equal. So we have the next, and this theorem is true in the countable dimensional case and uncountable dimensional case also. So we have this characterization for unital locally matrix algebras in uncountable dimensional case. Okay, now we consider example. First example, this is example of Clifford algebra. I recall definition of Clifford algebra. Let V be a vector space over field F, and characteristic of F does not equal to. And F small f from V to our field be non-generate quadratic form. The Clifford algebra, we denote the Clifford algebra by this symbol, is a unital algebra generated by the vector space V and Y and defined by the next relation. V squared equals F from V multiplied by 1 for all vector V from our vector space. And now if we have some basis of our vector space and I is number of is a set of all indexes, we can assume that this set of indexes is ordered. Then all possible ordered product Vi1, Vi2, and so Vik and 1 one can be defined as the product, is the basis of Clifford algebra. Clifford algebra is a unital algebra and locally matrix algebra. And if B an finite dimensional vector space, then the Clifford algebra is locally matrix, and Steinitz number of this algebra equals 2 to power infinite. Okay. Another examples to obtain more examples, we consider a generalization of Clifford algebras. Let now L be a positive integer, L greater than 1, and we consider field F if characteristic of F greater than 0. Then we assume that this number L and characteristic of our field F is coprime. So let C be an L's prime root of 1 and L be an ordered set. The generalized Clifford algebra Li is represented by generators xi and the next relations: xi to power L1 inverse to xi xg xi c xj, xi inverse xj xi c inverse xj, and this is called for all a and j. In this case, a less than j, in this case, a greater than j, a j from our set of indexes. I recall that our set of indexes ordered, so this is correct. And we also can consider this generalized Clifford algebra if we have the finite set of indexes. And in this case, we will see that this Clifford algebra Lm, where m is the number elements in the set in this finite set. Okay. So if you have generalization of Clifford algebra Li, this algebra is a unital locally matrix algebra, and ordered monomials xi1 to power k1, xi r to power k are form a basis of this algebra. Some properties of this algebra. This algebra does not contain proper ideals that are invariant under automorphism group of this algebra, and this algebra is semi-simple. This is also results from our paper with Oksana Mzushak. And so the next theorem, the theorem 3, the Steinitz number of a unital locally matrix algebra Li, whereas the set I is infinite, is L to power infinity. And from this theorem follows the next property of unital locally matrix algebras. If we have some Steinitz number, and this Steinitz number contains some prime number in a power infinity, then for any infinite dimensional alpha, there is a unital locally matrix algebra A such that dimensional of this algebra A equals alpha, and Steinitz number of this algebra equals to this Steinitz number. So we considered example Clifford algebra, and we show that for 2 to power infinity, there is an algebra such that Steinitz number uncountable dimensional locally finite unital algebra such that Steinitz number of this algebra equals 2 to power some power. From this theorem, we can construct all algebras of, we can construct locally matrix algebra, algebras, unital locally matrix algebra such that Steinitz number of this algebra will be L to power infinity. So we can construct for all primes prime number to power infinity. And from this theorem follows that theorem 4, so we can construct for any supranational number such that this supranational number contains some prime in a power infinity. And the next question, question very natural. Okay, if you have Steinitz number locally infinite locally finite Steinitz number, what we can say about this case? Is there unital locally matrix algebra A such that Steinitz number of this algebra equals to this infinite locally finite Steinitz number or not? So we return to this question later. And now we consider examples non-isomorphic algebras with equal Steinitz number. I recall that if from this theorem follows if we consider countable dimensional algebras, then countable dimensional algebras isomorphic if and only if the Steinitz number is the same. So now we consider examples where we have uncountable dimensional algebras. These algebras are non-isomorphic, but with the same Steinitz number. So first algebra constructed in the next way considers the vector space V. This is a space of all infinite sequences of complex numbers. Such that this condition holds. And we define F, the quadratic form, in the next way as a sum of IA square. So from this follows that this definition is correct. That's okay. And this vector space has an uncountable dimension. With this quadratic form, we define Clifford Clifford algebra. And this Clifford algebra uncountable dimension. This Clifford algebra has uncountable dimension. So now assume that I is the set of all indexes whose cardinality is equal to the dimension of the vector space V. And let now W be a complex vector space with basis Wi. Assume that G is a quadratic form on W, determined as alpha 1, B, I1, and so on, where alpha, this is coefficient from our field. Some number for our field. Okay. And we denote quadratic form in this way. And also we can consider Clifford algebra on this space V, W with this quadratic form. So we define two Clifford algebras. This is A, the first algebras, and B, second algebras. And from theorem about Clifford algebras, from this theorem, we have that the Steinitz number of both of them equals 2 to the power infinity. But these Clifford algebras A and B are not isomorphic. To prove this theorem, we show that these algebras has different. These algebras have different centralizers. Okay. So this is the main difference between accountable and uncountable dimensional unitary locally matrix algebras. So we can construct non-isomorphic algebras such that Steinitz number of these algebras equal. And now we return to question about infinite locally finite Steinitz number. So we construct two examples, and from these examples proves that for all infinite, not locally finite Steinitz number, we can construct some unitary locally matrix algebra A of a countable dimension with Steinitz number of this number. And next question, what will be in the situation where we consider infinite locally finite Steinitz number? So next theorem, for an arbitrary infinite locally finite Steinitz number S, there exists a unitary locally matrix algebra A of uncountable dimension with Steinitz number S. This proof of this theorem based on the theorem of Kurochkin. This theorem we can formulate as in the next form. Let A be countable dimensional locally matrix algebra with a unit 1, A. Then A contains a proper subalgebra, A 1A, proper subalgebra B, such that B contains 1 and A isomorphic to B. And now I will talk about primary decomposition of algebras. A unitary locally matrix algebra A over a field F is called primary if Steinitz number of this algebra equals some prime in some power. So equals P to power S, where P is a prime number and S a positive integer, or maybe as equals infinity. And we say that this decomposition of unital locally matrix algebra A, our field F, is a primary decomposition. Primary decomposition if each algebra AB is a primary. So Steinitz number of each of this algebra equals prime number P to some power. Kyoto proved that every countable dimensional unital locally matrix algebra admits a decomposition into an infinite tensor product of finite dimensional matrix algebras and admits a primary decomposition. Kurochkin and Kurochkin further studied existence of and uniqueness of such decomposition of unitary locally matrix algebras of arbitrary dimensions. In particular, Kurochkin formulated in his paper the next question: does every locally matrix algebra have a primary decomposition? And we give a negative answer to this question. There exists a unitary locally matrix algebra of uncountable dimensional that has no primary decomposition. This theorem directly follows from the theorem about existence of uncountable dimensional unital locally matrix algebra A with a Steinitz number, infinite locally Steinitz number. From this theorem follows the existence of such algebra, and if the algebra A admits a primary decomposition, then we can construct this primary decomposition as our number S infinite locally finite. This means that all of these are P less than infinity, and in this case we have that AP isomorphic to matrix algebra P to some power. This is a finite dimensional algebra, and in this case this algebra need to be finite dimensional or countable dimensional, but we know that this algebra uncountable dimensional. So from this follows that there exists a unital locally matrix algebra of uncountable dimension that has no primary decomposition. Okay, and in his paper, Kurochkin constructed an example of unitary locally matrix algebra of uncountable dimension that does not admit a decomposition into an infinite tensor product of finite dimensional matrix algebras. The example of Kurochkin has Steinitz number 2 to power infinity. And the next theorem, if I is the odd number, then Clifford algebra L. If L is the odd number, and then the Clifford algebra L R on the because this is the set of all indices is not isomorphic to a tensor product of finite dimensional matrix algebras. And the next theorem for an arbitrary infinite Steinitz number S, there exists a unital and locally matrix algebra A such that Steinitz number of this matrix A equals to S, and A does not admit a decomposition into a tensor product of finitely dimensional matrix algebras. So we have examples of algebras to any Steinitz number that we cannot represent as decomposition into a tensor product of finite dimensional matrix algebras. From this theorem follows that we have from this theorem follows that we have many examples of algebras that cannot be represented as infinite tensor product of finite dimensional matrix algebras. And also we can construct these algebras for any supranational number A or S, sorry. So this is all for today. Thank you very much for these references, and thank you for your attention.
Okay. We thank you for the nice talk. Do you have any questions or comments? You can simply ask. You can unmute your microphone and ask if you want.
Yeah, can you show? So
Okay.
please show the references, the biography. Yeah, thank you, thank you, thank you.
This is first page. Our main results with Oksana Basusyan published in these two papers.
Thank you.
And in a couple of days, the presentation will be posted together with the video. So you can wait a little bit to see everything once again.
Yeah, thank you.
Some other questions or comments?
I think there is a typos in the title of the talk. Please show again the title, the first page. Look at the name Steinitz.
Okay, there is.
Пропущена буква А, Steinitz.
Sorry. Yeah. Okay.
Some other comments? If no comments, yes, take the speaker once again for the nice talk and interesting talk. And I want to make an announcement for the next talks. The next talk will be the next Friday, but it will be earlier at 11 in the morning Bulgarian time, so 2 hours earlier. The speaker will be Arkadis Linko. He is from New Zealand in the moment. And if you go to the home page of the seminar, you can see the title and the abstract. And in 2 weeks, the same time, 1 p.m. Bulgarian time, there will be a talk by Natalia Yudu, and the title will be announced later. So in the homepage of the seminar, you can find all the program till almost the end of July. And then in August, we have a small break for a month or a little bit more. And in September, probably we will continue. But now it's time simply for chat. So you can speak in any language with anyone.
Okay, so I shall stop recording now.
Okay, yeah.